When we think of climate change, we often think of greenhouse gas emissions that create increases in temperature. And that is also the focus of most economic studies. Yet there is also the possibility of tipping points. After all, our climate is a complex ecosystem, and changes can often lead to further changes, creating a cascading effect. And one such example is the melting of Arctic ice sheets. Yet tipping points are inherently uncertain and hard to model. But my guest for today, Gernot Wagner, wrote a paper incorporating these tipping points into an economic framework and then analyzing their impacts. And Gernot is a climate economist at Columbia Business School and faculty director of its Climate Knowledge Initiative. He has written 6 books, including Climate Shock and most recently Geoengineering, The Gamble. And Gernot's research, writing, and teaching focus on climate risks, technologies, and policy. And Gernot holds a PhD and Master in Political Economy and Government from Harvard and a Master in Economics from Stanford. And I'm very happy to have him on as a guest today. He's someone whose research I greatly admire. I also highly recommend checking him out on LinkedIn, where he publishes nearly daily very insightful comments, and also his site, which I will link in the show notes. With that said, Gernot, welcome to the show.
Hi, Arvid. Great to be here.
I am excited to discuss your research. So maybe to start, what motivated you to write this paper on the economic impacts of tipping points in the climate system?
Well, a call from Simon Dietz, who is my co-author on the paper, one of 3 co-authors on the paper, to suggest we work together. More seriously, tipping points, for better or worse, have been part of the popular imagination, if you will, for a while. And, we can blame Malcolm Gladwell for that, right? So, he sort of, popped social psychology, right? So there are sort of lots of examples where small change leading to this rapid cascading massive overall effect. But pop psychology, I guess, would exactly go for that sort of thing, right? Like, maybe the butterfly flapping its wings somewhere and the hurricane follows, right? So, and now we're already with weather and climate and so on. And clearly there is something here where when you go to the Earth system, and now we are switching from Malcolm Gladwell to Tim Lenton, climate scientist, who a while ago by now. So this was 2008. He was the lead author on a really, really important paper that introduced tipping elements, tipping points, into the climate conversation. And the IPCC has picked up on this. The latest assessment report has a very good definition of tipping points: a critical threshold beyond which a system reorganizes, often abruptly and or irreversibly. As IPCC go, right? So, every word in this sentence was heavily negotiated. There were memos being written, committees formed, and so on. For example, the and or, right? Abruptly and or irreversibly, right? So, rapid change, right? The sort of thing we think about when we think tipping points. And then, irreversible comes in, irreversible in our lifetimes, irreversible
Exactly.
in, decades, centuries, and so on. Or, the Western Arctic ice sheet collapses, and we have, meters of sea level rise as a result. Now, okay, that's not abrupt necessarily in the sense of, next week, next month, next year, or even next decade. But is it irreversible if and when it happens? And or is it abrupt in Earth systems terms, right? It's not going to take billions of years. It's not going to take millions of years. It will take hundreds, thousands of years. Yeah, that is pretty abrupt in the the lifespan of the planet. And right. So tipping points in the climate system come in various shapes and forms, but they all share those characteristics. They are either relatively fast and or, to stick with the IPCC wording, right? Something flips The Amazon rainforest dieback, as an example, are a very different kind of tipping point from the Western Arctic ice sheet. But yeah, Amazon dieback sounds pretty scary, and it is, right? It has massive regional, massive global consequences if and when it happens. And yeah, that's clearly a tipping point that should rise to the sort of top category of most important changes one needs to grapple with, think about, that have these massive cascading effects, and that, yeah, are typically not included in sort of these climate economic damage functions where a bunch of climate economists, bean counters, go out and figure out what happens um, when
E-
temperatures rise.
exactly. It seems that, as you describe in your paper, economists were very and are very aware of tipping points, but kind of maybe treated them a little bit in more of an ad hoc way.
Yes, right. And okay, so now we are, yes, okay,
Uh,
happy to talk about my own paper, of course, right? Now we are okay, what's the contribution here? And full disclosure, so Dietz et al. This came out in 21, so 5 years ago by now. So what do we do there? Well, we go through the list of dozens of potential candidate tipping points. Um, we zero in on a finite number, 8-ish tipping points that we then go out and quantify, and we don't do it ourselves, right? So we integrate them into a consistent climate economic model. But the key bit here is we go to the earth science, to the climate scientists, and the underlying models they have to quantify the impact, to capture the impact, right? So it's not just sort of point estimates, if you will. It's not just like look at one line here that says temperatures rise, tipping point gets worse, right? That sort of thing. It is basically looking at the actually underlying equation, right? The Earth system's processes, the physics underlying those processes, and then incorporate that into our climate economic
yeah.
model.
And could you maybe give some more example? Could you maybe give some more examples of these tipping points?
Happy
Because
to.
you like
So,
because you mentioned you have 8, which I wasn't fully aware of all of them. Let's say, so I think it'd be really interesting to hear you comment on some of those.
so,
So
so
explain
I
what
mean,
they are.
okay, so it's quite a diverse list, and mentioned that Western Arctic ice sheet, or sort of ice sheets in general, right? So it's the Greenland ice sheet, and danger is a collapse. There's the Western Arctic ice sheet, and once again, it is basically that ice sheet collapsing, sliding first slowly, then increasingly faster into the ocean. So ice sheets is one, right? What's the main effect? It is sea level rise. And what's the economic problem, if you will? Well, it is coastal flooding. It is the need for massive adaptation that begins with seawalls, but it certainly doesn't end there, right? It might be giving up entire areas close to oceans. Okay, so that's one type. The other type is a second type is of carbon cycle feedbacks, right? And essentially, what that means is there are tipping points out there where a bit of warming, maybe not that small warming, but global average warming suddenly leads to a massive, broader change. So, for example, permafrost, a good example here, right? So there's permafrost, permanently frozen, boreal forests. There's a lot of CO2 potentially trapped into that frozen tundra, and if and when that melts, suddenly a lot more CO2, methane, and so on gets released, leading to much more rapid overall warming. Right. So carbon cycle feedback as one, as a second type of tipping process, tipping point here. And yeah, boreal forest is perhaps the best example here. There are a couple others, and actually, sort of Arctic sea ice is one. All right, so we all know from grade school, elementary school science experiments, if the ice cube floats on the water and the ice cube melts, the water level actually doesn't rise, right? Because Archimedes told us as much, I believe, in sort of fundamental science here. Well, turns out that there is potential carbon cycle feedback. Why? Because of albedo effect. So ice is bright white, reflects sunlight back, cools what is underneath. The open water, surface water, is darker, attracts heat, warms up the ocean even more, right? And sort of this carbon cycle feedback here ensures that Arctic sea ice might also be one of those tipping points, precisely because of the albedo effect and the overall effect on um, uh, the carbon cycle. Right? So that's the second type. Um, a third, a big one, and actually that's been in the news lately, is the broader circulation changes. So this is like the Gulf Stream, right? AMOC. I mean, Gulf Stream is what we call it, sort of loosely speaking, but really it's the Atlantic meridional overturning circulation, AMOC, AMOC. And right, if and when that collapses, and I keep saying if and when, by the way, right? So with enough warming, we will trigger those tipping points, right? So the exact time, the exact place might be in doubt. But yep, the scary bit here, if you will, is that up to a point we know if we keep warming the planet, 2 degrees, 3, 4, 5, 6, right? We will pass these thresholds. Or if we think we know that we will pass these thresholds. And AMOC is a good example because it's been in the news lately because a lot more science has gone into studying the processes, and specific word definitions matter here, of course. So we are not exactly talking about a complete collapse of AMOC, at least not this decade, even this century. But yeah, a 50% slowdown is massive. Right, and what's the effect? Well, the effect might be that Europe, Northern Europe, would actually get rapidly cooler as a result. Right, the sort of the classic story that the Gulf Stream brings hot air to warmer air um, to Europe, making northern latitudes livable in Europe, even though those exact same latitudes in North America are are frozen, Arctic, in Canada, and so on. And in some sense, ironically, right? Usually we talk about global average warming. In this case, the effect of this particular tipping point, the effect of this particular circulation change, massive circulation change, would have the inverse effect on Europe, right? Massively cooler. Which, by the way, this is a bit of a side note, perhaps, but this already leads to some of the difficulty here, right, of doing the science or doing the climate economics, if you will, right? Because maybe one effect of this AMOC collapse might be at least a temporary uh, uh, decrease in the effect of global average warming on Europe. Right? It counteracts the warming. Right? If warming is bad and an AMO collapse leads to cooling, well, I'm not going to say that the AMO collapse is good, therefore, but at the very least, there seem to be some trade-offs we need to consider. Right, and okay, and just to finish the thought, the classification of tipping points. There's a fourth, biomes, right? Rainforest, for example, Amazon dieback, massive natural capital degradation, ecosystem loss, right? And yes, right, that by itself is has possibly catastrophic regional effects, and of course also potentially catastrophic global effects.
And I think that's something I really like about your paper is you look at these tipping points in isolation, if I got it correctly, but then you also at some point study how they interact with each other and then their influence on the results. But before we get into maybe this the deeper dive, so you have then these eight tipping points which you identified. You then incorporated the science from the other papers, like in bringing it in into your integrated assessment model, and then you set out to see, okay, what happens then to economic outcomes.
Yes.
What then, how then did you work on the damages from the integrated assessment models? Like you've got these different tipping points, like how do you then study the economic impacts of them in
Uh, in this model, okay, so the model we created, and again, right, so this is together with co-authors, so Simon Dietz, Thomas Stirk, and James Rising, uh, putting together, creating this model. We call it the meta model, right? I always need a cute acronym here. But at the end of the day, it integrates these several different tipping points. And yes, this now allows for interactions between these tipping points and so on. But we basically look at the overall effects on climate damages with these tipping points compared to without, right? And it's not as simple in reality, of course, to turn them on and off, right? Well, as a modeling exercise in our model, that's exactly what we do, right? That's exactly how one tests the effect of a particular tipping point, or for that matter, all of them together. And the headline figure, if you will, is that our best estimate, and there's a difference between the mean and the median estimate here, of course. But the range, median to mean, is between 25 and 50% increase in the overall social cost of carbon. 25% for the median estimate, um, 50 for the mean, when one considers those tipping points, right? And I can tell you, well, okay, opinions differ strongly, right? So I can tell you, we're almost immediately accused of underestimating the importance because, oh wait, I thought tipping points are the end of life as we know it, right? So if you say that median social cost goes up at 25%, that's not a lot, right? That's a small change. Well, first of all, it's not a small change. It's a massive change. But equally important, yeah, it does not show, right, that, oh, these tipping points all mean, we all die tomorrow, right? No. I should immediately add that, right, so when I say this, the median estimate and then the mean estimate, which in fact is, twice as big, a percentage change in the social cost, that means that there is a very skewed distribution here, right? There's a massive right tail. And in fact, yes, there is a 10% or so probability of a doubling of the social cost due to those tipping points, right? A 1 in 10 chance that the social cost, in fact, increases by 100%, almost. And there's a 2% or so chance, according to our calibration, that social cost triples because of these tipping points, right? So there is a long right tail, a pretty thick right tail, to this distribution of the global economic impacts of those tipping points.
and I think that's the point when people say, oh, it's only between quotation marks 20 to 25. They often think of this really right tail, but it's in there is just you have probabilities for them, like the 2% or the 10% and the doubling and the tripling, which is massive, because the social cost of carbon is already very high, once we have the current estimates of I don't know if you have your preferred estimates.
For the social cost,
Yeah.
I mean, actually, funny you should mention that. But so it turns out, so actually, a later paper, also with several co-authors, including two from the Tipping Points paper, once again, Simon Dietz and James Rising. But this effort was led by Francis Moore. and was published a couple of years ago by now, also in PNAS, which is our synthesis calculation of the social cost. So, the synthesis of evidence yields high social cost of carbon estimates. The title is even longer than that. But that was our sort of let's add it all, and including tipping points, by the way, right? So let's look at everything that we can possibly quantify to come up with the sort of minimum, lowercase conservative social cost of carbon estimate. And once again, right, there's a distribution here, of course. And it turns out our estimate of the social cost is somewhere in the 280s, so $280 minimum. Um,
280s. Okay. Yeah. Yeah.
$280,
Yeah.
right? I mean, I think 283 to
Yeah. Yeah.
mention the falsely precise estimate here. But by the way, so this is based on hundreds, almost 2,000 different estimates of the social cost in almost 150 different published studies in the literature. And then we did additional work. We a survey of the authors of those papers, expert elicitation, and it's this re-evaluation of the evidence. And actually, it's actually maybe instructive to quickly mention sort of what we actually did there, which is how does science advance? Well, you take 80% of what people already know, and then you push somewhere, right?
Exactly.
You push in one dimension. And what that has what we've ended up with as a result in the social cost of carbon literature more broadly, is a whole bunch of individual estimates, that all often sort of go back to Bill Nothaus's dice
Yeah.
model, right?
Exactly.
A well-known base case, basically, and then they push on one dimension, right? And they say, oh, if one only does this one thing, the social cost of carbon increases by X%, right? And then somebody else starts with the same base case and says, oh, if you only do this one other thing, the social cost increases yet again, right? And so on. And it's really hard unless you analyze it all together, if you will. But it's really hard to say, oh, so what's the overall estimate of the social cost? What's the best estimate? Right, this is where integrated assessment models come in, but it's important to basically go to those individual studies, probe what they've actually done, right? Look under the hood of what they've actually done, and then, include the effect, the overall effect of each of those individual things one can do to the social cost, including tipping points, um, in an overall estimate of, again, right, there's a big distribution, there's a wide range, there's sort of this meta distribution here, or the synthetic SCC, the social cost of carbon, what we call it. And we end up with a number that has a large range, at least about 100. It goes up to way above 300, 350 dollars per ton of CO2, and the average is somewhere at $280.
I think there was also which is already exactly much higher than the 180 that was like the the update under
Yes, right.
that's kind of still was like the number in my mind, but I
This
imagine
is why the
this
280 is so important, right? So instead of 200, right, we are almost at 300 basically per ton of CO2. And right, again, this does include the tipping point estimates
yeah.
already. But right. So if tipping
which,
points, the
which also
median
shows how
estimate.
important which also shows how important they are, because once you get to 300, 20 to 25%, that's like, if I were just to take that benchmark of your paper,
Yep.
if you were to not include the tipping points, you'd be at like 240 or something. Or
Quick
yeah,
math. Yes, something
just
like
this
that.
very
Right? No,
simple.
it's a large impact, right? So I mean, tipping points matter. They increase the social cost. They lead to this right skewed distribution once again. Like the main figure in our paper, tipping points, is precisely that right skewed distribution. And they are clearly costly, potentially large economic impact. Also, and I think that's key too, a potentially large heterogeneous economic impact. Right? Not everyone is affected equally. Right, so Amazon dieback has bigger effects in the Amazon basin, of course, right? Brazil, Latin America, of course. AMOC collapse, right, has a bigger effect in Europe than anywhere else. And speaking of heterogeneous implications, it might even lead to some cooling early on, I mean, massive potential cooling. But early on, at least, it might actually decrease the overall cost here of higher temperatures. Well, because AMOC collapse might does lower temperatures in Europe, Northern Europe.
And I should also mention for the listeners, I will share the link to your paper, but there's a great graph figure 4 where you kind of like show it in the world, like the different changes and the impacts. Because it is, like you say, heterogeneous
Yep.
across the world. So
Um,
I highly recommend it. Also put that in the transcript with a figure. So
Good point.
um,
Good to be in a podcast where yes, listeners actually click through to the paper and look at the figure. And so
yeah, exactly. So generally they like the numbers. I think that's also why they listen to this one. Maybe then one question we've you've talked about quite a bit, but one thing that I always like to ask then is before we get into the more technical is, so you wanted to write about tipping points. What, what was like, maybe was there like a big surprise you had like during the research, like ex ante, during, or sometimes I like to see like where were your priors when starting the paper, and then
yeah.
did something shift in your thinking along writing it?
So I mean, yes, and maybe actually, one maybe a surprise to me at least was in fact, hey, there are some trade-offs here, right? And not, oh, climate change is good for Northern Europe, right? No, it is not. But yeah, this one particular tipping point, AMOC collapse. What's its overall effect? And it looks like it at least takes the edge off the global average warming component, right? Like, there are other effects of climate change, of course, and frankly, this is how science advances, of course, but um, there are in fact other effects, right? Extreme weather phenomena, extreme precipitation events, and so on. And right, so the typical story, of course, is of if a system goes out of whack, right? Leaves its sort of balance, right? Long-standing balance, that sort of the 10,000 years, this Goldilocks period that human civilization developed in. Um, then yes, there might now be effects that, frankly, our model doesn't capture. Or actually, I should say this. I should say this differently. Right? It's not just there might not. There definitely are effects that our model doesn't capture. And sadly, most of those effects probably point in the direction of those tipping points being worse than are currently estimated.
Yeah. Then maybe let me ask, because like you said, it was published in 2001, and then you kind of, I maybe I should, kind of say advocate to integrate them more in these other integrated assessment models. Like, how have you seen this kind of literature develop since then? Because I also imagine what you did wasn't easy, bringing in them in. But here, I don't know. So that's an open question there.
Um, I mean, our model has certainly been developed further, and I should say full disclosure. So this is primarily two the co-authors, Thomas Stirk and James Rising, who have done quite a bit of more work, and actually together with Simon. So I guess I'm the only one not included in this from the original team, and somebody else, Drew Schindel. Um, they have now revisited some of that original tipping points work and expanded it to methane. Um, and basically, right, so methane is a faster acting greenhouse gas. Its impact is not just on global average warming, well, not primarily on global average warming, but on the rate of change. Right, so you might expect now that if you look to methane as a key greenhouse gas leading to rapid changes, right, then a look at tipping points might get you some interesting results. And frankly, yes, I mean they found that there are in fact much larger effects here on a short-term time horizon than for CO2 alone, right? Which isn't much of a surprise, to be clear. But yeah, so integrating methane into this tipping point story, of course, leads to interesting results. And frankly, I think that's a key advance in the last 5 years or so. I should also say, and this is sort of two more, I would say, advances, if you will, and they don't both go in the same direction. So one is, as I mentioned Bill Nordhaus before. So he is famous for lots of things, but he in fact won a Nobel Prize, shared a Nobel Prize in economics, won it in climate economics for basically his contributions to the field, which I think is fair to say anchored by him developing dice. This sort of famous, relatively simple model, and the simplicity, of course, is key as well here. Um, and I am happy to say that his the latest iteration of off dice, that he's worked on with a co-author, Lint Barrage, at ETH Zurich. So the two of them have recently published the latest iteration of Dice, um, and it turns out their base case now includes tipping point damages calibrated based on the Netter model we developed 5 or so years ago. So yeah, that's how science advances, right? So is that the end all be all now? Is Dice suddenly the best climate economy model out there? No, it is not. Um, but does including the effect of tipping points provide a step in the right direction? Yes, I would like to think so. Now, to be clear, right? Like, if you ask me what's the social cost of carbon, I would not go to that latest version of DICE. I would, in fact, go to a synthesis analysis that includes DICE-based estimates, of course. But that leads to this
Yeah.
$280-ish. That's, of course, much higher.
I think I have to do an interview on that one because I think also it's a really good paper to kind of see the dependencies. And we also talked a little bit with Richard Toll in that episode. So maybe I also want to be respectful of your time. Maybe to close off, is there something we haven't talked about that you would like to still bring up? We didn't really touch income inequality, but
I mean, there's lots of things we haven't
exactly.
talked about, but frankly, let me start with a caveat of sorts, if you will. And the simple summary is not everything is a tipping point. Quite literally, and I should say this. So my very first paper on tipping points was with a climate scientist, actually, named Bob Kopp at Rutgers. It's fantastic, and the two of us together with a couple others um, wrote a paper sort of on the definitions of, right. So tipping elements, climate economic shocks. How does one incorporate them into economic analysis? And in some sense, that sort of set me at least off in that direction, the research agenda. It was published in 2016 at this point, so a while ago. Okay, Bob Kopp got the gang back together recently and wrote a paper saying that tipping points confuse and distract from what's actually needed, from urgent climate action. I mean, that's literally the title. Tipping points confuse and distract from urgent climate action.
Okay.
And honestly, I'm with him on this. So I wasn't a co-author on that paper, but up to a point, I have to agree. Which is that I mean, obviously it's of course true, right? So not everything is a tipping point, right? That's of course true. But I think it's also true up to a point that when one focuses on tipping points, right? And you and I just did, and thank you for that. Of course, that's important. But yeah, in some sense, we talked about these massive global changes, which may detract from the sort of like the slow burn, if you will. And when I say slow burn, that's literally a book, right? That's literally a book title. Ji-sung Park, good friend, a great economist himself, who wrote this book called Slow Burn, which came out some like 10 years after Climate Shock. So Climate Shock was like 2015, Slow Burn was a couple of years ago. Um, and I would say the two books basically say the opposite. They're both right. Right, so climate shock wasn't just solely on tipping points. It was about fat tails and so on, but it was about these low probability, high impact, right, massive overall, fat tail events, tipping points, if you will. Like they're not the same, but like loosely speaking, these massive changes. And then comes along Jason Park, writes a book called Slow Burn, and it's about these tiny, almost undetectable small changes that, when you add them up, of course, lead to massive overall impacts. And that, by the way, you should say, so Jisung was in fact a co-author on a peer-reviewed paper on precisely this that I worked with him on, and a couple others. Patrick Bearer was the lead author of this paper on productivity impacts. And essentially, what we found, and what Slow Burn also talks about, is that um, one day, one day of temperatures above a particular threshold, 90 degrees, 90 degrees Fahrenheit, 32 degrees centigrade, one additional day lowers annual payroll by 0.04%.
Okay.
Right?
Yeah.
That's a small change. But we're talking about one hot day here, right? One additional day above 32 degrees centigrade in a given year lowers annual payroll by 0.04%, right? That's the slow burn, right? That's not a massive global tipping point. That's just a single hot day,
Yeah.
right? And okay, again, right, like not to turn it about this other topic now, this particular conversation, it's still about tipping points, right? But yeah, Bob Kopp is right up to a point when he says that not everything is a tipping. I mean, he's 100% right on this, right? Not everything is a tipping point. Yes, of course. Well, up to a point, focusing exclusively on tipping points detracts from precisely those sorts of effects, like these tiny little productivity hits every time we have a hot day, right? And of course, we are projected to have many, many more hot days because of climate change. So, in other words, it's about both, right? It's about massive global Earth systems, tipping point style changes, and quantifying them is important, yes. It is also, of course, about taking these productivity hits, those mortality morbidities due to hot days, due to higher than average temperatures, or especially temperatures hitting a particular threshold. And this boiling frog analogy is actually, or is wrong, right? Frogs are smarter than that. They actually jump out of the water. They don't boil alive. Turns out they jump out, right? We may not be jumping out. Right? We may be the ones who are getting burned alive here through this process, through this slow burn process. And again, right, I'd like to think that both of these are right. Unfortunately, it's both about the climate shocks, the tipping points, the fat tails, and about those slow burn processes. Both cost us in terms of health, and yes, of course, in terms of economic GDP impacts as well.
Awesome. Well, then, yeah, I like that a lot because it's like your 20 to 25% increase is still on a very big number.
Of
That's
course,
like
yes.
so it's like don't forget about the other thing. So thanks so much. I think that was a really really good one. So I get, you know feel free to go. Do you feel like it might confuse then the tipping points? Do you see that like happening, that it just often now obfuscates like the smaller things? Or
So I would say, okay, the pendulum, I would say, has swung quite a bit toward the OMG, climate leads to these massive catastrophes. And to be clear, it does, sadly, unless we act, right? Meanwhile, yeah, right. Many more hot days, many more days above 90 degrees Fahrenheit, 32 degrees centigrade, and so on. Many more tropical nights, many more sort of these productivity losses. So once again, right? Speaking economics here, so hot days have different effects as well. They're very direct effects, right? Um, well, there are in fact productivity losses here that we ought to uh, quantify, we ought to include in our damage calculations, and maybe sort of to bring it all back together, right? At the end of the day, in order to estimate the climate impact, in order to properly quantify climate risks, climate uncertainties, yeah, we have this metric called the social cost of carbon, and that metric should reflect both the slow burn on the one hand, the tipping points on the other, and the many, many other impacts in between.
Awesome. I think that's a great way to end it then. I think that was a really good one. So, Gernot, thank you much for coming on. I've really enjoyed this conversation. It's got me a lot of new thinking and actually also leads for future podcasts, like exploring exactly the slow burn, the synthesis you did. Maybe I'll contact one of your co-authors. So thank you
Please.
so much for coming on. I really appreciate it.
Thank you. That was fun.
Just